the screen?
Yes, sir.
So in the last class, we were talking about unsteady state flow over a flat plate. So what you have here, you have something like this. So you have a flat plate here. On top of that, there the fluid uh, to a infinite, you can say the thickness. But this need to be solved for a finite thickness actually. So we are considering that thickness of fluid is extra, means very large. Now, in the beginning, actually, this entire thing is at rest. So in that case, velocity everywhere is zero, and g is acting means vertically downward. So what you have here, so these are the, you can say, assumptions we are considering for that. That wall also infinite in the length, actually the flat plate actually x y z, as you know here, the this now the flow is parallel to the plate everywhere, so you are just moving your plate with some constant velocity. So in the beginning, at t equal to 0, so you have velocity everywhere the 0, and then suddenly you are setting this plate in motion actually, so and this will move with some velocity. And now flow is completely parallel to the plate, means you are moving the plate only. So in that case, the whatever velocity would be generated only in x direction, there would be no velocity generation in y direction as well as in the z directions. That's what we are considering the assumption part here. Now, this is something, the pressure variation along the length of the plate is constant because it is open to atmosphere. So you are not applying any pressure gradient in x directions. So everywhere you have the atmospheric pressure or a constant pressure on that, right? Next assumption, you are considering that fluid is completely incompressible and Newtonian with constant property. And flow, we are doing it for laminar flow part. And flow is completely in two-dimensional actually, so you don't have any movement in z direction, so derivative with respect to z is also 0. So if you will apply your x momentum balance for the in x direction, because the motion of the plate is only in x direction. So this is our momentum balance equation for Newtonian fluid. So if you will simplify this, you are cancelling this term. I hope you know why are you cancelling that del u upon del x term.
Yes, sir.
Because this is from fully developed characteristics, right? So
Yes,
then
sir.
you are considering that no velocity in y direction, so v is getting cancelled. And along the width also, that means there the two things you are considering, means either you are considering that width is too large, so therefore the velocity variation in z directions of x velocity is not very significant. So in that case, you are cancelling this term 0. Okay. So you are considering del u upon del z term is 0 in that sense here. So now gx, because g is vertically downward and x is horizontal, so gx is also 0. You are not means applying any pressure gradient, so del p upon del x term is also 0. Then del u, so if you will simplify that, you are solving it for unsteady state, so velocity can change with respect to time. So what you have here, that del u upon del t would be mu by rho del square u upon del y square. So this is a partial differential equation of second order, so that need to be solved. And that mu by rho is termed as nu, and nu is called kinematic viscosity of the fluid. Now, what you have here that at this particular time, equation number one, same type of momentum balance. Also, you can do the y direction, so you can find a pressure change, how the pressure will change along the thickness of the fluid. This is second thing. You can do the Z momentum balance. So in case of Z, you will come up with this thing, and from here del P upon del Z. So no variation in Z direction. So that's quite obvious because pressure is the only function of distance or depth of the fluid only. Because in that case, if there are no variation of velocity, so therefore this term would also not change. Now let's understand what will happen to the plate as it was at rest. So at rest means at the time when you have t less than equal less than 0. So in that case, you are not applying any velocity to the plate. So this is the condition. This is your y direction, this is your x direction. So entire fluid is at rest. So there won't be any velocity component here. So this would be the situation in the beginning at just t less than equal to 0. What will happen at t equal to 0, because you are just about to apply the force just to move that plate with some constant velocity. So in that case, the plate would have some velocity just at t equal to 0, but you are just setting it. So t equal to 0 means just setting it. In that particular time, the plate have the velocity. Rest of the fluid are not able to move because you are just setting it only. Then at a time when you are just will increase your time, let's say t just greater than 0, it could be in microsecond, nanosecond, we don't know that part. So if means anything just t greater than 0, so this would be the situation in that particular part, that fluid in contact of the plate will start moving with the velocity of the plate, that v naught or u naught. And as you will go inside the fluid upper side, so your disturbance or let's say velocity generation inside the fluid will keep on decreasing and decreasing, and there would be a height, it will become 0. After some time, what will happen that if you will move it to the longer side, there would be another velocity that can be generated. Let's say draw that picture also. So maybe this way, that another condition would be of something like that. Correct? But is this line correct or not?
So can you please repeat this part?
Let's say at t equal to greater than equal to 0, this would be a velocity profile at some time. Now let's say after a particular time, I am drawing you two lines. Can you identify them, but which one is true? That one line is here, something like this. Another line, let's say, of something like that. Are both the lines correct or something is wrong? Hello?
Yes, sir.
Are both the drawn line, the red lines are correct, or anything is wrong with these lines?
So after some time, shouldn't the profile become linear?
No, it would be always okay. but it won't be the linear thing. So that is the different part. I am just okay. And rest of the part, I'm not talking about the linearity. So linearity is okay. Non-linear, it would be the flow over a flat plate would always would become just like a parabola only. Linear thing never comes. Actually, you already got the expression when you have solved it previously. Anyone else can say about these two lines? Are these fine or there's something wrong with these lines? Just quickly. So this is what you have drawn at a particular time. After that, you have drawn. This is also fine. This is close to that. Now, next condition, you have drawn something like that. Are these two profiles are fine? That first one is this and second one is this. Okay, if you cannot find the answer, so I will tell. You have started that plate with some velocity v naught or u or some velocity. So at the time t greater than zero, this is what that fluid in contact of the plate will gain the velocity v naught only, right? Hello.
Yes, sir.
Yes, sir.
So no matter how long will you drag the plate, the fluid in contact of the plate can never gain any velocity which is more than the plate velocity. Yes or no?
Yes, sir.
Yes, sir.
So therefore, in that sense, this second profile, this one is not at all justified because this shows that this particular fluid after some time has reached the velocity which is almost twice the velocity of the plate, which is not possible, right? So this part is not there. So only thing it would be the profile would be always something like that, and it will only thing it will keep on moving off something like this. This is maybe another time, maybe another time further, and maybe after that it may reach to another velocity, something like that. Okay. I've not drawn it means correctly because the freehand thing, only thing they cannot overlap each other. What will happen over the period of time? The momentum will try to percolate inside the thickness of the fluid. So only thing, this top fluid will start gaining some velocity. Correct or not?
Yes, sir.
Bottom fluid will always would be the velocity of the plate. So therefore, all profiles at a different time would always meet to the at this point only because the plate velocity is fixed. Now let's see what are the boundary conditions you have here. As we have explained it in figure, so we can do it here also in that way. So what you have here. So there you have this part that at t less than equal to 0, your velocity everywhere u is 0 for all y, no matter whether you are here or here or here. For all y, velocity is 0. This is the initial condition. Now when you set it in the motion at t greater than 0, so at just t equal to 0, what will happen at y equal to 0, your velocity of the plate would be the velocity, same velocity would be of fluid. So fluid will also gain the velocity of the plate, u naught. At y equal to infinity means at top of the fluid, you are much more far away and you are talking about the infinite thickness of the plate, fluid, sorry. So in that case, your velocity of the fluid at infinite thickness would be zero, because no momentum can be able to percolate the infinite thickness of the plate or fluid, right? So these are
Yes,
the two conditions at extreme and at plate, and that would be at infinity conditions. So now we can non-dimensionalize it, because the idea behind that, we want to convert this partial differential equation somehow to the ordinary differential equations in one variable, so that we can solve it easily. So first part, we are doing the non-dimensionalized velocity. So you are dividing instantaneous velocity divided by maximum velocity of the plate. So which is u upon u naught. So based on that, you can substitute this in your original equation. Original equation was del u upon del t is nu del square u upon del y square. So in that case, you are substituting at the place of u, you are putting phi into u naught. So if you substitute that, you will get this equation, that del phi upon del t would be nu del square phi upon del y square. So that is one thing. So here the nothing has been changed much. So you that means that still have two variables in the denominator, the derivative. One is del t, another one is del y. But you have non-dimensionalized it. Now you can find non-dimensionalized boundary conditions. What are those in with respect to time? Because this is changing with respect to time. So phi at y equal to at all y at t equal to 0, your plate is entire fluid is at rest. Therefore, your this u upon u naught term would be 0. So u is 0, u naught have some velocity, so that would be 0 here. At y equal to 0 means you are at plate only, just like this at here. At y equal to 0, you are here. Now, for that case, your velocity of the fluid would be maximum. That would be u naught, divided by u naught would be 1, right? So in that case, you can write this for that. This is your phi at y equal to 0. So your velocity u would be u naught. So both the means this will cancel. You will become 1 here. This would be condition for all time t, at as far as the t is greater than equal to 0. Now greater than 0, not equal, and now at phi at y value infinity at the top of the fluid, your velocity would be always 0, because you are talking about infinity. So 0 upon some value would be always 0. So these are your non-dimensionalized velocity boundary condition, which is with respect to t and y. Let's see further what can we do. We want to non-dimensionalize our distance coordinate. So from the previous one, you can say that phi is function of y, t, and nu, right? These are the three variables there
yes,
in
sir.
previous equations. Now for that, we can club these things and just to make another variable, which can be a combination of y, t, and nu. So for that, we can non-dimensionalize this distance y. So we can write the y upon a function nu into t and under root of that. So this would become a dimension of distance only. So because nu is meter square per second, right? And this would be time. So per second will get cancelled. You will get meter square. Root of that would be meter. And finally, you will get meter upon meter. So you will get a non-dimensionalized distance, right?
Yes, sir.
Yes, sir.
So this is called a eta. So eta, you are the defining non-dimensionalized thickness of the fluid, which is y upon nu t. 4 came just a mathematical factor just to bring your entire solution in a particular form. Therefore, 4 factor has been put. Otherwise, it's not required. Now you have clubbed y nu and t into a one new variable, which is another non-dimensional thickness, the eta. Now you can say that now you can write this was your phi, right? So your phi is a function of y nu t. Now y nu t are clubbed in terms of eta. So this is now your new function, right? That phi is a function of eta only, right?
Yes, sir.
So this now you can rewrite your equation there. So you have a term there del phi upon del t in your original equation number 3. Now you can find the derivative of that from here. So you can write d phi upon d eta, because you can find now total the derivative of that, because the phi is the only function of eta. And then this way, I think this is the way you are finding the derivative of del phi upon del t. So if you do that, substitute the expression of the eta, that y upon under root of 4 nu t, from here differentiate this. So if you differentiate this, finally you are ending up with this equation there, that del phi upon del t is coming out to be this much only, that 1 by 2 d phi upon d eta eta upon t, correct?
Yes, sir.
Now another variable in that equation number 3 is del square phi upon del y square. So first we can calculate what is del phi upon del y. So you can find from the same way that d phi upon d eta multiplied by del eta upon del y. Substitute the means expression of eta there, y upon under root of 4 nu t. So if you differentiate this, you are getting your del phi upon del y would be d phi upon d eta multiplied by 1 upon under root of 4 nu t. Now you can differentiate this thing again, thus just to find the second derivative. So you are having del square phi upon del y square. So you are the differentiating this term again. And now for that you will the differentiate this, and you are ending up with this equation, that d square phi upon d eta square will be that d eta upon this del phi multiplied by this. Now you already have expression of this one from here, d phi upon d. So you can substitute there further here. So you will get this expression, the from the previous one. Club all these values, you are getting that d square phi upon del square phi upon del y square is coming out to be that 1 upon 4 nu t, and then you are getting this d square phi upon d eta square. Is that fine till here?
Yes, sir.
Yes, sir.
Right. So now you have this, you have the expression for del square phi upon del t, you have the means expression for del square phi upon del y square. Substitute these two expressions in your equation number 3. This was your equation number 3, right? So substitute all these here. So if you are the substituting this here and rearrange it, you are ending up with this equation, that d square phi upon d eta square plus 2 eta into d phi upon d eta would be equal to 0. So this is now your you can say second order ordinary differential equation now, which you can solve, I hope, with some comfort as compared to the PDE, right?
Yes, sir.
So now you can find your non-dimensionalized boundary condition again in terms of eta. Eta is what? Eta is the nothing but y upon under root of 4 nu t, right?
Yes, sir.
That was the eta which you have considered. So now at phi equal to 1, what phi equal to 1? What is phi? Phi is u upon u naught, right?
Yes, sir.
So what is your first boundary condition? That at y equal to 0, your velocity of the plate is equal to the your velocity of the plate is u naught. At y equal to 0, fluid velocity would be also u naught. So that phi is 1 at y equal to 0. So therefore eta is 0 for all time which is then equal to, greater than 0. So therefore that y upon under root of 4 nu t at y equal to 0 would be always 0. Correct?
Yes, sir.
Yes, sir.
Next boundary condition which you have there, that at y equal to infinity, your velocity of the fluid is 0. So therefore phi is 0 and eta would become infinity because y is going to infinity. So y upon under root of 4 nu t would also be infinity, right?
Yes, sir.
Yes, sir.
So these are your two non-dimensionalized boundary condition now, and this is the means equation which need to be solved. So you can consider that let's say that d phi upon d eta would be equal to means another function psi. Now you can substitute here that psi would be from here, the d psi upon d eta would be 2 eta into psi equal to 0. So here you can write that d eta would be equal to minus 2 eta into psi. So you can separate the variables here. So you can get d psi upon psi would be minus 2 eta into eta square, correct?
Yes, sir.
Now this can be integrated easily. So if you will integrate that, you will get ln psi would be equal to minus 2 eta square by 2 plus a constant there. So you put here maybe in terms of ln c1. Now this entire term, this one, you can write here ln of exponential of minus eta square, right? Correct
Sir,
or
your
no?
voice is breaking.
Uh, okay, so others also.
Now it's fine, sir. It was breaking before.
Okay, okay, fine. So now you have here, this is the term you can write in terms of ln again. So you can write ln exponential of minus eta square. Now these two terms can be clubbed into one term here. So ln c1 exponential of minus eta square. Is that fine?
Yes, sir.
So from here, you will get your expression of psi would be like this. The psi would be c1 exponential of minus eta square. Correct?
Yes, sir.
Now now the psi, what do you consider for psi? Psi is d pi upon d, right?
Sir, your voice is breaking again,
This is
sir.
the let me reconnect it actually. But these days signal is very bad. Sometimes it goes to zero actually. So let me reconnect. Can you hear now?
Yes, sir. Now it's clear.
Okay. So this is what your psi. Now you have psi. You have considered that d phi upon d eta is psi. So you substitute that again here. So this was the psi you have considered, that d phi upon d eta, which was equal to this. Now from here you can integrate this thing. So if you will integrate that, you will get psi equal to phi, sorry, phi equal to this constant C1 integration of 0 to eta exponential minus eta square into d eta plus C2, right?
Yes, sir.
Yes, sir.
Now here you have these are the two constants C1 and the C2 that need to be solved from your boundary conditions. So what are your boundary conditions? That at phi equal to 1, your eta was 0. So if you substitute that phi equal to 1 in this equation, which you have this one, so you are getting that C2 equal to 1, right? Correct?
Yes, sir.
Now you have another boundary condition that phi equal to 0 at when eta tends to infinity. So if you will do that, you will get 0 equal to 0 to infinity exponential minus in this eta square by 2 into that d phi d eta plus 1. So if you solve that, you are now this is the something which we can do at last, not here. So don't get confused with this. So from mathematics, this comes 0 to infinity term exponential minus eta square by 2 comes to be under root pi by 2. So we are not doing here. So you can write here in this format here, that in terms of pi, if you want to the right here, so you got the constant C1 equal to minus 2 upon root pi. So from there, your expression of phi is 1 minus of minus 2 upon root phi, 0 to infinity, 0 to eta, this one minus eta square by 2 into del eta. Now you can substitute this here, this one which you have considered from here, this one, substitute this back. So if you substitute that, you will get this one. You can write phi equal to 1 minus of 0 to eta, and another one is 0 to infinity, right? So this entire term is being treated as this total term, this one is treated as the error function. So your phi comes out to be that phi is 1 minus of error function of eta. So this is the means error function of eta. Okay.
Yes, sir.
Now you can substitute what you have considered for phi, what you have considered for eta. So phi was u upon u naught, right? This one. Error function is fine, that at the place of eta you have y upon of under root of 4 nu t, and this total thing is called 1 minus of error function. This total form is called complementary error function, which that defined at error function c means complementary error function y upon under root of 4 nu t. So this was your expression for now. This is the something which you can understand from here. Now, can you read it? I hope you can something. If you will read it, you will come to know here that complementary error function eta is a monotone, the decreasing function that goes from 1 to 0 only. Means highest value can be 1, lowest value can be 0 only, and it drops to my 0.01 when eta tends to 2. When you will substitute this expression here in this one, in this expression, if you will substitute eta equal to 2, this goes to a value of 0.01. Because this is coming from purely mathematics, that when you will put eta equal to 2, this error function, this goes to a 0.01. Now, if you will substitute here 0.01 here, what will happen? That complementary error function is this. So the 0.01 means at this particular place, this whole thing is getting to 0.01. Now, in that case, the u would be that 0.01 multiplied by u naught, right?
Yes, sir.
So this would be the value here. So that you can means now you say that define a boundary layer thickness. So boundary layer, the definition is what? Boundary layer thickness is when the velocity of the fluid drops to the 99% of initial velocity. Correct or not?
Yes, sir.
So if you will calculate the difference between u naught minus of zero point zero 0.01 of u naught, what would be that? 0.99 only.
Yes, sir.
Correct. Now from here you can calculate that that delta. You have considered that delta, which was your film thickness, is 4 nu t, right? That was your non-dimensional thickness, which was eta something. Correct.
Yes, sir.
Yes, sir.
Now from here, if you will see that, so this is being treated as your diffusion of the momentum thing, and this you can calculate 400,000 nu t, and from here you can calculate that this is the boundary layer thickness. Now here boundary layer thickness is considering to the square root of this the time, that how much time you are giving here, and it will change in terms of square root of that. So that's, and now from here only you can tell that that from where that 99 concept of boundary layer thickness has come. You might have seen in all boundary mean the layer thickness, when your fluid reaches to a velocity which is 99% of the original one, and that's called your boundary layer thickness. Okay.
Yes, sir.
Okay, sir.
So try to means the do it means yourself, and now you would come to know that somewhere I can tell at the end here now. Here you have eta square by 2, right? And if you see back, here somewhere in our expression, here you have eta square only. Correct or not?
Yes, sir.
Now you might be wondering that from where this eta square by 2 has came.
Yes, sir.
Correct? So just think about that. So because if you are adding this in this integration for an infinite term, so generally what they have taken the averaging of this function. So if you are adding anything to the infinity part, does it matter what are you adding? Just a simple layman type of the language. If you are adding something to infinity, does it matter what are you adding?
No, sir.
Because finally, if you are keep on something adding to infinity, you will ultimately reach to the infinity answer. Correct or not? Hello?
Yes, sir.
So what they did here, they have taken the averaging factor of that, because you are talking about infinity, and practically they have just taking the averaging of that. Why the averaging would help it? Because it will bring your this total expression in terms of that error function, and error function is mathematically defined, because otherwise for that you will get this, you have converted this entire expression into that 0 to infinity exponential minus eta. So here if you will see the book here, suddenly they have put here a bar here. So this is average thing here. They have done that part here. So averaging they have done by doing by one by two terms. Otherwise, there no other expression for that I could not find so far. So don't get confused from here that suddenly it was at this place eta square thing, and now suddenly it has become here eta square by 2. So it is just to averaging this thing, and that's all only. So to convert this entire expression in terms of error function. Now I can tell you that why that 4 was considered in the previous one. If you would not have considered that 4, you will not end up with this type of format, and you will get something else which is not, so you can say, the mathematically defined function actually. So to get the answer in a particular format, that 4 factor was being considered, that your non-dimensional eta thickness was y upon under root of 4 nu t, just to get the expression only in this particular format only. Okay.
Yes, sir.
So that is the only the logic, just to consider a 4 factor here. Otherwise, there was no other the logic in that one. So this way, you will say that your all expressions on flat plate part is completed.